Now we'll see the second question for synchronous generators. Okay, so this is also the second midterm question, right? That was done or was conducted for those who didn't take the first midterm. All right, so this question involve the calculation of losses, unlike the previous examples. So this synchronous generator is rated at 13.8 kilovolts. It has 50 MVA power, 0.9 power factor lagging, operating at 60 Hertz. It is 4-pole and Y connected to the mains, and has a synchronous reactance of 2.5 ohm and armature resistance of 0.2 ohm. And at 60 Hertz, the losses are 1 megawatt and core losses are 1.5 megawatt. So when it is running at no load, the terminal voltage measured is recorded at 13.8 kilovolt when field current is actually 3.5 ampere. So all of this information, sometimes you don't use it all, okay, of them. So you have to carefully select which one is you're going to use, okay. So firstly is, what is the speed of rotation of this generator? Now, the speed of rotation of generator's shaft is like the previous one, that we actually find out what is the synchronous frequency lah, or synchronous speed, sorry, using this equation, okay. So the electrical frequency times 120 divided by number of pole. So 120 times 60 over pole is 4. So it is running at 1800 RPM. Okay. So what is the magnitude of EA? Okay, at rated conditions. Okay. So it wants EA at rated conditions. So first of all, we need to we know that we can find EA through the equation of EA equals to V phase plus J or plus REIA times REIA times JXSIA. Okay. So this equation is coming from per phase equivalent circuit. Okay. So if we take a Kirchhoff voltage law and take a loop throughout the circuit, we will get this equation. Okay. So from this, we know that we have to find V phase. RA and XS is already known. And then we need to find how much is IA. Okay, okay, now for a Y-connected generators, we know that IA is actually equals to IL. Okay, and IL we can actually find from output power equation, which is, for example, P out over square root 3 VL cosine theta. Okay, we can also find from first of all finding how much P first. Okay, so P out is actually S cosine theta. Okay, so S is in this case 50 MVA. All right, and then cosine theta is 0.9. This is power factor lagging, so we get 55 MVA. 55 megawatt. Okay, so IA is therefore 45 megawatt divided by square root 3 VL cosine theta, and the line voltage is 13.8 kilovolts. So is 45 megavolts divided by square root 3 times 13,800. Okay, and then cosine theta lah. Okay, so cosine theta is 0.9. Then you will get IE equals to 2092 ampere. Okay, all right. So the power factor for IA is actually arc cosine, or the not the power factor, the angle between I V phase is actually the arc cosine of the power factor, which is minus 25.8 degrees. So IA is basically 2092 minus 25.8 degrees. Okay, so V phase is actually VT divided by square root 3. Okay, this is Y connected, and it is 7967 volts. Alright, so EA now is simply V phase plus RAIA plus JXS IA. Now 7967 plus RA is 0.2 ohm times IA is 2092 minus 25.8 degrees. Okay, minus 25.8 degrees plus J 2.5 ohm 2092 minus 25.8 degrees. So this will give you 11,544 to 23.1 degrees. Okay, so this is the magnitude of the internal generated voltage. Okay. So how much, the last question is, how much steady state power and torque must the generator's prime mover be capable of supplying to handle the rated condition? Okay, so this is quite a lot of marks, 7 marks. We need to find out first how much power in each of the component of the power flow. Okay, so first of all, if we calculate the output power, we know the output power is S cosine theta. So S, the output is 50 mega VA times the power factor is 0.9. So this will give you 45 megawatt. The copper losses is 3IA squared RA. So this will give you 32092 squared times 0.2. So give you 26 megawatt. The friction and windage losses is given 1 megawatt. Core is given as 1.5 megawatt. Stray losses are still negligible here, it doesn't say anything. So P in is the summation of all this. Okay, so P out plus the copper losses, friction and windage losses, the core losses, plus the stray losses. So this will give you 50.1 megawatt. Okay. Alright. So the input power from the prime mover must be this much lah, 50.1 megawatt. Okay. Now the applied torque, okay, must be the input power divided by the speed, okay, of the generator itself. Okay, so 50.1 megawatt. So we know the speed of the synchronous generators is 1800 rpm just now. We calculated. Okay, so this total will give you 265.8 kilonewton meter. Okay. So this is the input that must be given to the shaft of the generator to give you the rated, or the rated output that is stated here. Okay, so it's quite what we call large, the amount of, we're looking at 265 kilonewton meters. This is a very large torque to be applied, okay, at the generators to produce, okay, because the power is huge as well. All right.